Welcome, my name is Bo Galle. I am professor in optical remote sensing. In the following two presentations I will discuss measurement of gas emission as opposed to gas concentration. Most standard in situ instruments measure concentration, while many environmental issues rather require knowledge of the emission rate. I will here discuss some measurement strategies aiming at measurements of emission and give some examples of different approaches to meet this challenge. In the first presentation, the examples will cover measurement of gas emission from volcanoes, megacities and industry, while the second presentation will cover examples from landfills and shipping. The concentration of a gas is usually expressed in mass units, gram per cubic meter, or as a mixing ratio, parts per million. Concentration is a useful unit in many applications related to atmospheric chemistry or health effects. However, in many other applications the goal is to determine the emission of a gas, expressed as gram per second, or the emission factor expressed as gram per gram fuel or gram per kilometer. The gas emitted from a source will be dispersed during transport to the recipient. It may also undergo chemical transformation. Using a meteorological model, taking into account also possible chemical transformations, the emission may be calculated from knowledge of the concentrations measured at the recipient by running the model backwards. This is, however, not possible when the meteorological conditions are complicated, which is often the case. Thus, alternative methods are necessary. One such method is the previously described mobile DOAS technique. Here the total column of a gas above the instrument is determined by absorption spectroscopy using the sky as the light source. As the plume is traversed, the total amount of gas in a cross-section of the plume is determined, and after multiplication with the plume speed, the emission is obtained. In the following, I will present three different applications using this measurement strategy, and will start with volcanoes. Different gases are dissolved in the magma at a certain depth below the volcano. The most important volcanic gases from environmental impact point of view are carbon dioxide, sulfur dioxide, hydrogen chloride, and hydrogen fluoride. When magma rises towards the surface, or even erupts, the pressure drops and the gases are released. Depending on the volume of the magma involved, the gas emissions may be severe. As an example, the fissure eruption at Hullorán on Iceland in winter 2014-15 emitted initially about 700 cubic meter lava per second, yielding a sulfur dioxide emission of around 100,000 tons per day. This is about twice the total sulfur dioxide emission from human activities in Europe. The environmental impact of this emission was severe on Iceland, with hourly averages exceeding the World Health Organization limit for days and weeks of a large part of Iceland. Elevated concentrations were also measured all over Europe. The measurement of these high emissions were made from the ground by DOAS instruments using the sky as light source. Measurements were made from the ring road surrounding Iceland, yielding the overhead burden of sulfur dioxide, which together with meteorological information determined the emission rate in kilograms per second. The eruption gradually decreased over its 6-month duration, yielding a total release of around 11 megatons of sulfur dioxide. In comparison, the 1783-84 Lucky eruption on Iceland emitted about 10 times more lava, and therefore also 10 times more gas over its 8 months of duration, and caused severe damage on the environment. An estimated 60% of the grazing livestock and 20% of the Icelandic population died as a consequence of the gas and ash release. Also, the agriculture in Europe was badly hit, with severe famine for several years. It has even been suggested that the environmental impact in Europe of the Lucky eruption may have been an important trigger of the French Revolution in 1789. The same methodology, mobile DUAs, can be applied to study emission from large areas, for example megacities. In this example, the instrument was mounted in a car that made a full circle along the ring road number 5 in Beijing. The total path was about 100 kilometers, and the emission of sulfur dioxide and nitrogen dioxide could be simultaneously measured. By making a full circle around the city, the amount of gas transported into the city from the surrounding could be subtracted from the gas transported out, and thereby the emission inside the circle could be determined. It could be seen that the emission of sulfur dioxide was considerably higher in spring than in fall, probably due to more coal-fired heating in spring, while the traffic-related nitrogen dioxide emissions remained relatively constant. Many industrial activities emit gases that are harmful to the environment. Some of these gases are emitted through well-defined vents and chimneys and can then be readily monitored by in situ instruments. However, some of these emissions have a distributed source and constitute so-called fugitive emissions. Such emissions are hard to quantify with standard instruments. An example of such emissions is hydrocarbon emissions from a refinery being released from leaking valves and tanks, wastewater dams, process areas, and similar. We here apply the solar occultation flux method. This is an approach similar to the mobile DUAS technique described above. However, as the mobile DUAS technique is limited to measurement of molecules having optical absorption in the wavelength region given by the blue sky, UV to visible, the measurement of many molecules of industrial relevance requires infrared spectroscopy. Thus, the sun is used as a light source. By means of a solar tracker, the direct light from the sun may be focused into an infrared spectrometer, and the slant column of various molecules along the path between the instrument and the sun may be derived. As the solar tracker dynamically keeps the sunlight focused into the spectrometer as the instrument is moving, transects of the industrial plume may be made in analogy with the mobile DUAS measurements, and thus the emission may be determined after combination with wind speed at plume height. In this way, the emission of several different gas molecules from an industrial plant may be simultaneously quantified. The results may then be compared to emission inventories, often obtained from standard tables. As these tables may not fully take into account leaks and other deviations from ideal conditions, they often underestimate the real emissions. Thank you for listening. I hope you have found this first presentation about emission measurements interesting. In next presentation we will focus on emission measurements using tracer gas and also discuss methods to obtain emission factors.